I think I'm going to do lots of flooding today because I'm just so out of practice. And it's going to be on camera. So we will be 100% off-grid today. Dave! So that's the electrical side. Also to note, solar PV panels out the front as well. Kilowatts. 33 kilowatts of input. This really feels like I'm defusing a bomb. Which goddamn wire do I cut? Red one, it's always the red one! Copper coffee cup. Copper coffee pot.
Proper cup of coffee in a copper coffee pot.
Proper cup of coffee in a copper coffee pot.
Okay.
Okay, hello guys. So here at Heat Geek HQ, we've got a pretty efficient system installed, heating system that is. It's actually work in progress. We've got a lot to do to it still, but the bare bones are there. And pivotal to finding out how efficient it is, we need to be measuring the system. We can't just take a guess. If we can measure exactly what's going in the system and how much thermal energy is coming out, we can find that out. And I'm very excited today because Tristan from Open Energy Monitoring is coming in to install all of his kit so we can build like a dashboard and see exactly what's going on with it. So open source monitoring, so like I guess anyone can add their own APIs and stuff and build their own thing. It's a sort of a self-customizable app that can manage and measure solar PV, EV charging, heat pump monitoring. We're going to be doing some different stuff with them. So we're doing solar thermal, which isn't on here, and it's not a normal thing to heat with solar thermal, which we'll be showing today. That we're doing something else. I think these guys basically they were just involved in some of the forums. It's sort of DIY energy forums. And they were chatting, they saw a need, and they've just kind of set up this company, and it's kind of started to take off. And they've got, people just absolutely love these guys.
We try and trick him with the...
Give him one of our hot sweets. Yeah. We've got these sweets that have got ghost chilies in the middle.
Oh, amazing.
Yeah.
I'm a big
We tell people they're cool lime flavour. It's a cool mint chocolate. It takes a while, because, you normally don't show this bit.
We'll time-lapse this bit of the video. Hasn't really hit yet.
Okay, it does hit.
Oh, there it is, the first swallow. Yep, my voice is going.
Ooh. Should we go see if that's hit? Oh, it's an electric car, so most likely. How's it going? We're recording straight off the bat.
Great to see you.
Yeah, good to see you too. So I'll introduce you to these guys as well. Did you know Dave last time?
No,
Dave's my graphic designer.
Oh yeah, that's me.
So all the funky graphics he does. Harrison does our YouTube basically, or is going to be doing more of our YouTube.
What gang?
And I'm me. Tea or coffee? Oh, this is my. This is my mug. Yeah, he needs that. Yeah, it's all good. We haven't got it's like the whole industry is just absolutely nuts at the moment. And so I literally can't afford to go on holiday. We will at some point. Have you guys been getting away or?
Glyn, who I work with, he's currently down in south of France, but he's converted an ENV200 electric van into a camper van.
Oh wow!
Sort of his sort of thing, and he does videos about it on YouTube.
Oh, it's on YouTube. What's his? Do you know what his channel's called?
It's Glyn Hudson.
Okay.
Zero Carbon Adventures. He did have a blog, Zero Carbon Adventures, but he sort of turned that into a YouTube thing.
Oh wow! How's he only got 2,000? Subscribe to Glyn Hudson, guys. This looks like an awesome channel, and he's only got 2K subscribers, which doesn't seem right.
So I think.
Hi, Glenn. Right, so let me just quickly run through what we've got installed and show you exactly what we're measuring today. A quick rundown of what we've got here to run our heating is, instead of heating our radiators with a heat pump or with a gas boiler or whatever else we've got installed here, we do use a heat pump to heat our radiators, but primarily on this wall out here, we have solar thermal tubes. Now, solar thermal tubes collect heat directly from the sun. They play on one of these little collectors and heat the tube up on the back, and they're evacuated tubes, so they have no air in, like these tubes here, and then we pipe that to our buffer in there, and then we pump our radiator water from the buffer in there. So our heating, rather than being ran by boilers or a heat pump, is heated by the sun for free. So on the south wall, we've got our tubes. Roof. Excuse my childish drawing. We've got our PV. Solar PV to generate electricity. This is obviously pointing up at a 45-degree angle-ish. These have little collectors in them. Here's a zoomed in version. It's got a little plate, and we've just rotated these, so these are angled 15 degrees up towards the sky. So in the summer, obviously you have a very high skyline as the sun moves over. In the winter, the sun has a much lower kind of arc in the horizon. So because we've pitched this to pick up maximum yield during winter, and winter's when we obviously need heat. We don't need heating in the summer. It maximizes its generation in the winter. And then when it comes up high in the summer, these are less efficient. But what you get is, actually I'll set up another one. This axis is your yield, E for energy, how much energy you're going to generate out of it. And this is the time of year, January, December. If you have a summer pitch, as you normally would, you'll get a graph that looks like this, bell curve. If you go for winter pitch, you're going to be peaking much lower in the summer, but you're going to get more in the winter. And if you're aiming for heat generation in winter, as we are, because we're trying to absorb this heat energy to heat our radiators, this is a much better pitch. What we can also do, and what we're starting to do with this, we need to sort of tweak it as we go along, is we've oversized our tubes. The tubes might generate too much power in the summer. However, these tubes have got in them what's called therm protect. So Viessmann have patented this technology. They basically shut down when they get up to 90, 95 degrees, so they stop absorbing. Other tubes you can't do that with. But what that means is we can oversize our tube, and this is called clipping. We can clip off this maximum and it won't absorb that. But it means by oversizing it, we're getting higher yield in the winter. Obviously this graph isn't accurate, but that's why we've got them on the wall rather than the roof. However, on the roof, we do have PV. So the PV, that's electrical solar panels, comes down, it charges up our battery first. If the battery sees energy leaving the building, the battery drinks up energy from the PV, and if it sees energy coming back in, it will expel the energy and try and minimize the in and out of the building. So it acts as a buffer. So this PV energy comes to feed the battery. Once the battery's full and the demand in the building is catered for, so all the lights and computers and whatever else, any spare electrical energy then goes to our eddy. And the eddy, let's do a little eddy picture here, diverts the spare power into this immersion element here. And then once that immersion element's up to temperature, whatever you set it to, it sends it to this immersion element. I have to give my terrible drawing. So any spare PV, it charges the house or the property, and any spare, it puts it in our big heat battery, which is just a buffer. So that's the electrical side. Oh, also to note, solar PV panels out the front as well, and that's facing west. So that's that. The solar thermal, which is taking heat energy from the sun's rays, solar thermal is 80 to 90% efficient. PV, 20 to 30% efficient. So obviously per square meter, this is generating a lot more energy, and in the winter it will be able to perform a lot more efficiently, which is why we've gone for this kind of setup. So that simply is piped to a coil in the bottom of our buffer and is just continually heating that buffer. And our heating is pumped off that buffer. I'll have to draw another diagram for that though. There's our solar thermal coil. In our buffer, we also have cold water main that comes in here, goes around another coil, about 30 kilowatts. We've made it extra big to cool down this lower chamber here. So by cooling down that lower chamber, we keep that coil nice and cool, and that solar thermal array is much more efficient when it's cool. So that goes in, it then comes out, it then goes back in again via another big 30 kilowatt coil, and it pops out the top. It leaves this slug in here for the heating and just takes the absolute hottest heat from the top of the buffer to use for washing up and stuff. So we've got our two immersion elements in there as well. We've also got a tapping here and a tapping here for the heating. These are all joined together so we can turn off any one of these at any one time and draw at any height. We're just drawing off at the top for now because we're kind of experimenting with the whole thing. The whole thing's experimentation. And this just goes to a pump. Sorry, the picture's getting ever smaller now, which pumps around the radiators. If this isn't drawing enough heat from here and the temperature starts to drop, our heat pump comes on. So all as we have there is, where I drew that pump, on the outlet of that pump is a zone valve. That zone valve shuts off. The zone valve for the heat pump comes on and just turns on to weather compensated heat pump. So that's it really, that's kind of how it all works. And it's all sort of centered around this big buffer which stores completely free energy. All of the energy from this, there's no electrical, because remember, whenever we're absorbing solar thermal, we're almost certainly going to have some electricity to drive the pump for the solar thermal array and the central heating pump, because they use, in total in combination, they use about 80 watts, which is nothing. So yeah, that's it. I haven't got a car. Well, we've got a family car, but I only live up the road, so I don't have a work car. I ride to work every day. Do you want to go?
Yeah, that'd be amazing.
Okay, let's just pause work. Have some fun. Still got steering wheel.
Check up my body, join the flow.
Is it you building a ramp?
Well, why not? I don't think it's going to make. We need to. Going to give that up. I only thought about this last night because I hadn't booked one of our engineers to be here to cut in any of the stuff.
Okay.
And I hung up my tools 3 years ago, so I'm going to have to dig around in the garage and find some old rusty tools to cut in the heat meters and stuff. We can go out and get anything we need to get.
Okay.
But you know, I'm quite rusty on so. Just zoom out with the camera because it's going to be quite embarrassing. So obviously I'll help. I'll get the heat meters in, and I suppose you do
and then I'll just
whatever it is else you do,
connecting it all up essentially,
and show us how it kind of operates.
Yeah.
So when we're measuring energy, we'll show you in a bit. We're essentially measuring the flow and return temperatures and the flow rates, and using mass flow rate calculation, linked to mass flow rate calculation. One of those sides. I've done a video on it, and essentially doing that to measure how much energy is being moved from A to B. Is there more to come out? And then, when you supply this kit to whoever, this is normally a self-installation thing?
It is, yeah. So you get your plumber to put in the heat meters
Yep.
and so on, and then a customer, if they're like enthusiast householder, they could install the rest of it. So it would just be basically connecting up to the MBUS outputs and so on.
I mean, even so, the heat meters are compression joints. If you're an advanced DIY, you could probably do the heat meter as well. But you know. Okay, cool. So this is a flow meter, obviously.
Yeah. So Sharky.
So obviously measuring flow rate for mass flow rate, and then we'll measure. So that'll go flow or return. Does it matter as long as it's the right way around?
Usually on the return, but you can
keep it cooler.
You can configure them for either flow or return.
Okay, cool. And then, so as long as you know the flow rate and know the difference in temperature between the flow and the return, you'll know how much energy is collected or dropped off at the other end. Very simple. These are the temperature sensors, right?
Yeah, so that's another similar one. Cam strap.
Okay, so that's an inch version, and this is a three quarter.
Yeah.
And then it comes. So you can look at this monitor and or this speaks to a central receiver, is it, or?
Yeah, so both of them have got MBUS outputs, so we'll just be wiring them all onto that same sort of digital output.
So even if the app was down or for some reason you didn't have internet, you can just check to see the generation.
Yeah, that's the nice thing about it.
Yeah, I think we'll put the heat pump one up there. That's all wonky because I went up there yesterday and to touch a valve. I stood on a box and it collapsed under my weight and I pulled the entire ceiling down. So just ignore the mess up there.
He will fix the drywall now.
Yep, so I've got like a 28mm bit of pipe here that will work nicely. So yeah, that one for heat pump, that other one for solar thermal. Got one for cold water.
Yes.
Oh, you got a third one.
Using a Seeker. When you see these on lots of like Mitsubishi systems,
Okay.
but it's
So how come
it's a
this
different
one's...
type.
Yeah.
Essentially, it'll give you sort of a number of pulses per litre of water passing, as well as a flow rate.
So how come you haven't just used one of those type ones? What's different about cold water? Is it pressure or what?
So these both are ultrasonic meters, and they're particularly fussy about the water being at a particular pressure and having no air in it, so no air bubbles. And if there's any of that in there, they just don't give you any readings. But you can obviously control that in a closed system really well. So my thought was that we'd probably get problems with that.
Yeah. Without doubt. If they're fussy about air, cold water obviously has air naturally in it, where it's compressed and then decompressed at nearer the points of use. That's Henry's law. We've got it in our channel somewhere. When it's pressurised, it absorbs oxygen and air. And when it comes depressurised, it releases the air, so it's diffusion, and then the air comes out of solution. So that sounds very sensible. And the pressure here will fluctuate loads, as everyone in the area showers in the morning and then doesn't midday.
I've done a lot of testing around the heat metering side, but not on drawing the heat out of hot water.
We are not new to beta testing, that's fine. Right, so I'll cut in these 3 valves, and then we just put that... I could put this in the ceiling. I suppose it would be probably quite handy to have it on show. I think I'm going to do lots of flooding today, because I'm just so out of practice. And it's going to be on camera. Right, I need to go and have a look in the garage to see what tools I've got, because I haven't touched a tool in a very long time. Not in that way. Oh, Betsy here hasn't seen the light of day for a very long time. I actually bought this about 15 years ago, this tool bag. Done really well. I need to go and get a hose. He probably wasn't expecting to come to a installation company and no one have any tools or anything to just do any work at all. But that's the way we are. Everyone's out on site.
I've got a multi-tool in my camera bag if you want that.
Oh, great, perfect. I need to get one of the guys to come back. You know you're our best installer and the nicest. You know you're our best installer and the nicest. Yeah. Could you pop back to the office and just rescue me quickly, because I've forgotten how to plumb and I don't have any tools and I've got some plumbing to do. Thanks, Dave. Yeah, it's fine. All right, mate. See you in a bit. I don't do that anymore. I haven't even got a drain down hose. So, and he's got everything. We've got like 5 vans and they're all fully kitted out. And I've just been writing quotes for the last 3 years.
Yeah.
Which is nice.
Yeah.
I say it's not. I really like being hands on the tools, because especially since I started the channel, most of the stuff you learn comes from being on site and trying to make stuff work. Yeah. And as I've come out, I found that harder to keep, be part of that circle. You kind of slip behind, to be honest. Like the most knowledgeable people in our area, the guys in our industry, are the guys with the hands on the tools. Yeah. The guys in the office are nowhere near. Yeah. And I'm unfortunately slipping into that bracket. I have to be a theoretical expert instead. Just another little run through, I suppose, for you guys. We've got the meter itself, which counts the flow rate, and a flow and a return sensor, and this also transmits the signal out. That's going to go on the 28mm pipe up there, which is the flow and return from the 2 heat pumps out there. So whenever they're on and generating, Tristan is going to measure the current they're drawing, electrical current, and then measure the heat leaving, and then it can work out the exact running cop and feed it into the big sort of software package. This is for the solar thermal, so let's take this through to the solar thermal area. Right, okay, so that's the bit he needs to put here. Is there anything else he needs to put here? I don't think there is there? Come on, Dave, don't be shy. There he is. If I knew I was making a movie, I would have dressed up. They call him the Hammer of Hong Kong. He did a lot of filming in Asia. We won't talk about that later. So we're installing heat meters. This has got kind of a heat meter thing built in, but trying to interface it and get it to work with like a bigger app and stuff is difficult. So we're trying to monitor all our different energy sources to measure what's coming in and what's going out and where it's going, so we can fine tune it.
So that is taking the temperature, feeding to a receiver, sender, and then you can send it to your phone or your laptop.
Yeah, exactly.
You've got valves off sections, haven't you, there?
Yeah, problem. Where I want to install this, we've got this huge, great, massive. In fact, you guys need to see the size of this radiator. It's ridiculous. So this ginormous radiator is to heat this room. We have got an air-to-air heat pump to heat this room, but it's not quite man enough. And the heat from it just isn't quite as comfortable because it's not radiant heat. You're heating the air, not the objects within the room. Radiant heat just is more comfortable. So we got this huge oversized radiator so we could run at nice low flow temperatures and maximise our COP. So that's great, and that literally plumbs all the way in, goes right the way through and comes out the other side, and just a globe valve to balance on the end. That's a globe valve. That's in another couple of our videos. So that's great, and that's going to really maximise our COP from our heat pump. However, our problem is where we're going to install this. That radiator comes off before, so that's going to suck all the heat out the air pump, out the air source heat pump, and we're not going to be able to measure it. So we're going to have to uninstall and reinstall all of that pipework when you come in to.
Today?
Not today.
On a Friday?
Not today. It'll have to be on the weekend.
Okay, yeah, I'll take
No, well, this isn't plumbed in yet, so when we come to plumb it in, we'll just take off the T's from further down line and then come back round.
Yeah.
So just whack it on the flow and return there before it tees to go outside, and then it will measure both heat pumps. We've got 2 heat pumps out there, by the way. We haven't plumbed in the second one, so we'll think about that when we come to doing the second one. Are you all right with installing that? It's pretty simple, some compression. Cool. Right. Let's ignore that.
Something on that one there.
When we originally designed this tank, we put in all these centre pockets so we could watch the stratification and thermocline climb up and down the tank. So this is going to be part of our measuring. We're going to measure each point to see what it's doing when it's doing it. And that's the other reason we've got this cold coming in here. Solar thermal works best when it's as cold as possible. This cold pipe, cold water mains, comes in and cools down that bottom coil.
Yeah, so these are just digital temperature sensors.
Yeah.
We'll just put them in each pocket.
Right. Oh, Patrick's here. Hi, Patrick.
No, that's Dave. Hello, guys. Got to put some stuff in the fridge.
Hello, guys. So this is Nathan from Beta Teach. We've actually just agreed with Nathan that we're going to sponsor their next podcast for 12 series. That's right, is it, Nath?
That's right, yeah, you're going to be season 5 sponsors.
Anyway, what do you ring for?
Was that being recorded?
Yeah, all of it's being recorded. We might not, I don't know what we use and what we won't. We're just recording everything and just seeing what comes out at the end.
Don't record this bit, but
What we're doing here is we're just running bus cables between each point. So this system uses Modbus.
MBus.
Oh, is it MBus?
MBus, yeah.
MBus. So a bus connection is it's just a language. This speaks the MBus language. And bus cables, rather than sending a 240 volt supply that might signal on and off or something like that, this just sends a little frequency down a cable, speaking a language, and we to run our data points. So one of our data points we're taking is the amount of electricity that we're measuring that the heat pump's drawing. Another data point is the amount of energy that's coming out in heat by measuring the flow and the return and the flow rate. We can measure how much heat is there in kilowatt hours, and we'll send that down the bus cable as well. You can send this information down the same cable, so you can have that data point, 2 cables, Modbus cable coming to this one, and that can join onto these 2 cables, Modbus cables, and just 2 wires can go back to there, back to the central hub, and that central hub will be able to know, it will be able to listen to both data inputs and decipher between the 2, even though there's only 2 wires. So like amazingly clever, but actually really simple as well, because you're just running a 2-core cable. This is a 4-core, we've got spare in case. So we're just running little data points from our, or cables from our data points back to the central brain or hub. And then what Dave's doing here is installing the heat meter. So that's measuring the heat. That's the data input here. The data input over there is the electrical consumption of the heat pump. I need a drill. Oh no, we're gonna have to move Dave's desk and lift up the floor to get through to the next bit. My soft, moisturised hands are getting scratched. I might need to cut a hole in the ceiling. What's that, about 400 or 500 mil? 450? So I'll do it about 450.
Yeah, I'd say that's about 450.
Ew, where would I have put that? Ooh, okay. Oh, there's something down here. That's not good.
What is it?
There's some sort of box there that... Oh, there's...
Yeah, my box.
Oh!
Uh-oh.
Oopsie daisies. Oh my god, there's a whole fuse board down here. I was literally going to drill through that. We found a hole. Dave, come in here. Let me get a torch on it. It must be redundant.
So we need to take it off.
Okay, right. Well, on we go.
You guys work in the office here at HeatGeek. Is it normally this chaotic?
It can be, I guess. Maybe not so much drilling, but yeah,
Yeah, there's often quite a lot of people around.
Yeah. A good chaos.
Only occasionally drilling.
Yeah.
This is so boring. It's part of the job.
What's next?
This is what electricians have to live with every day. So here we're going to install this electrical meter, which is basically measuring the amount of electricity that's going out to the heat pump outside. So we're measuring the amount of electricity going out to the heat pump, and then Dave behind me over there is installing the heat meter, which is measuring the amount of electrical or thermal energy that's coming back, and then you can find out your COP. How efficient your system is. Oh, and while we're doing this, please remember to subscribe to see more content like this, and hit like on the video. If you hit the little bell icon as well, you'll get notified every time we release new stuff, and you can kind of keep up to date with what's going on. Just for the record, I'm not an electrician, and this really feels like I'm defusing a bomb. Which goddamn wire do I cut? It's the red one, it's always the red one!
This is beautiful. And then we take that, work that into me, give you a good old rub. Nice and hot. Yeah, hot and spicy meat. Yeah, boy.
Pet pack. I bet this is barbecue stuff for Patrick. Oh, what's this? This looks fun.
No.
By the way, guys, if you like this sort of vlogging style content, just let us know in the comments below and we'll do more of it. Dave!
Dave, stop filling up. Turn it off. Where's it coming through?
The union up there.
Go. Just union. You got some towels, Dave? I missed all of the electrics quite well.
So Dave isn't very good at plumbing. Just didn't do a joint up.
No, it's done up, just not
spilt water.
Perhaps as tight as it really wanted to be.
You know you're our best installer. Well, that's going to be an embarrassing thing to put on YouTube, isn't it, Dave? So, Tristan's just finishing up there. He's going to connect up that last sensor. We're going to gather some data over the weekend and come back Monday and take a look at the dashboard. So, see you then. Welcome to Monday. Let's have a look at the data. Okay, guys, here we are. Moment of truth. We're going to have a look at the live results of what we've been installing and measure how our heating system works. So, yeah, let's take a look.
This is just over the weekend now, 2 and a bit days of data, and it's looking really good, isn't it?
Yeah, well, there's no way I'd have expected that. So we've got very old single panel radiators installed upstairs. We haven't upgraded them for the heat pump yet. So it's 5 degrees outside, and at the moment it's 3.5 cop.
And that's at 40, almost 44 degrees, isn't it?
Yeah, exactly. Like, that's incredible. By the time we get that massive radiator in and upgrade the radiators upstairs, we're going to be hitting over 5, I would say, during this time of year. Yeah, it's going to dip to 4, 3, late 3s when it's -3, but it's -3 very rarely. It's this kind of temperature a lot more often, and we're going to be hitting over 5. I think we could be looking at a near 5 SCOP potentially, and we've got cavity wall, uninsulated cavity wall. And this isn't a special building, so this just goes to show what can be achieved with modern units. What's the 2.6? Is that its current?
It's currently producing 2.6 kilowatts.
So we're getting, it's 5 degrees outside today, and we've got 2.6 kilowatts of free energy just being sucked in from our solar thermal tubes on the side of the building, of just pure free energy. But so like that's a mental amount. We're gonna, I don't know, what time is it now? It's 10:20 now. Soon I'm going to turn on the solar thermal heating, and I'll let it assist. Let's say we end up with 70% of this building heated with solar thermal today, and the remaining 30% from the heat pump at a cop of 3.5. That's going to mean out of our heating demand, only about 7% or something like that's going to be generated by electricity. However, that 7% of heat is going to be generated by our 4 kilowatts of PV on the roof. So we will be 100% off grid today, provided the sun keeps shining. And actually, we'll probably be exporting back to the grid.
Some of these power spikes go up to like 33 kilowatts.
33 kilowatts of input.
But just very briefly,
Yeah. Whoa.
And the flow temperature was up to like, was 98, which seems like...
Oh, well, hold on.
Wow.
So is that 98 degrees?
Is that right?
Yeah, that probably is right,
like,
yeah.
It's kind of got that water up to a really hot temperature, and then it's just pulsed the pump on briefly.
Yeah,
so
it's just cooled it down. Because temperature isn't relative necessarily to energy, because if you have a small amount of water and you get that to 98 degrees, it's not a lot of energy. You could bring up a whole mass of water by 1 degree, and that can have loads more energy in. So that's something kind of important to understand. I don't know whether to turn on the solar thermal before, because it's going to assist no matter what you do.
Okay.
I'm going to turn it on now. Right, bear with. Right, so solar thermal heating is turned on now, assisting. So, well, actually, we should see the heat pump dial back a little bit, unless I'm completely wrong, obviously, which is possible. I may have turned it on too early out of impatience, but I kind of want to see the result. And if it doesn't go the right way, I'll just turn it off and then I'll turn it back on again. Would it be worth us giving a live link so anyone can come in and see this anytime, or is that what you had in mind anyway?
Potentially we could do something like
We could integrate it into your website in some way potentially.
That'd be amazing. Okay, so you guys are seeing a condensed version of this conversation. We're going to post a separate video of this full discussion because it's quite long to put in this particular video, and we'll post that up later. Also, if you're interested in seeing this data in this graph and you want it on our website, just comment in the comments section below, and we'll see what we can do. So what's happened here is it's now 11:33. The heat pump's backed off loads since when I put it on at 11:05 or something. It went from, the heat pump had 729 watts input and it dropped down to 513 once I turned on the solar thermal store. However, the upstairs immediately overshot and turned back off the thermal store. So that's not really helping. That's why you see another little blip up and down here. So I'm just going to turn off the heat pump completely and just watch to see what happens with just heating the building with solar thermal. See if we can continue to heat with it. So I'm just looking at this data. We've been leaving it, because I've turned on the solar thermal, I want to heat the building with solar thermal, and I didn't really understand what was going on. And now if you have a look at this graph, let's get rid of that legend. This here is the flow temperature from the heat pump, and this is the power output. The power output's dipping way below zero. So what must be happening is, I've turned the heat pump off at this point. What's happening here is the solar is going back through the heat pump every time it's coming on. Every time the solar thermal buffer is injecting heat into the heating system, it's going round the heat pump, which is giving us a negative heat pump coefficient. So the zone valve to the heat pump is either not wide in or it's permanently open for some reason. I'm going to get a ladder or some steps. We did have a zone valve to stop the flow going to outside when we didn't need to. Yeah, here's the zone valve. Oh, this ceiling's getting some torture. Here's the zone valve. Oh, the zone valve is wide in. So why are we getting flow outside? The zone valve is jammed open. So this whole time it's been on, and it shouldn't have been. So the solar thermal has essentially just been sending heat outside to the heat pump for no reason. I suppose it kept it defrosted, and that's been like that for about a year. That's good. Right, I need to test this now and make sure it opens the zone valve when it's running, or if it's just been jammed open because someone couldn't get it to work. That's not right. The reason the zone valve doesn't open is because one of our employees can I slack my own company off? Thinks that's how you install a zone valve. That's not how you install a zone valve. Nothing like that. Well, that answers that then. We found out the zone valve was permanently wide open, which is fine for a weather compensated system, but it means when the heat pump's on, when the solar thermal's on, it also circulates back round the heat pump. The only small amount of efficiency it means it will lose is the pipe work that runs out to the heat pump, which is a very, very short run. But it's just something we don't want, and it's corrupting our data and making it look like we're exporting energy when we're not. We just need to get that zone valve to open and close as it should do. So the absolute beauty of this graph, we could have been exporting heat to outside and running heat around that evaporator for no reason for weeks and months. In fact, we were, and we didn't know. But now, it's only a tiny amount of heat that it's losing, but it's showing up immediately on this graph as a sore thumb. and I've traced it back and found that cable. The minute you've got like a slightly complicated system, it can show up stuff like this, which is obviously really handy. Immediately, this has been beneficial and made our system more efficient. And we haven't even finished installing it yet. Let's go back and get my toolkit. Stuff's got real. So our solar thermal has just stopped generating. It's 100, 200 watts. What time is it? It's 3:30. 3:30, and our solar thermal stopped generating. The heating's been solely run from solar thermal since 11 or something like that. I would have said earlier on in this video. The sun's gone in. Actually, if there's no watts, we should see shadow on our solar thermal. Yeah, looks like it's dipped behind that house. Look, the sun. Yeah, so we've just gone in. You can see the far end has got a bit of sun on it, and this 90% of it is in shade. So we've just lost our solar thermal, and let's take a look at the temperature up in the office. Right, so we've still got 21 degrees in here. The sun's gone in, no more solar thermal energy. However, that whole tank is full of hot water. We're going to see what temperature, and that will continue to heat our radiators for the next, well, let's find out how long. That cylinder is only pulsing heat once every 30 minutes or so. So the rest of the heat that's coming from the solar thermal is just being drunk up by the buffer. The bottom of the buffer's at 35, the middle of the buffer's at 36, 37, top of the buffer's at 37. So we've got essentially a full buffer of 37 degree water there, which will pulse around the building and heat the building for the next, I'm going to guess for the next hour or two, we'll have free heating, even though we're not getting any solar thermal. Right, okay, it's the end of the day. It's now 20 to 6, so we've had a full day of heating. Tristan's been fiddling around, getting everything sort of finished and putting in some extra sensors. We've got some room temperature sensors, things like that. And we can have a look and see if this just ridiculous heating system actually does do anything. Okay, yeah, so that to me is just awesome, how you can see the sun, arcing over in the sky, and exactly at 12 o'clock when because those happen to point directly south, is our peak input of 42 kilowatts, which is amazing.
4.2.
4.2, sorry. The zone valve we installed for the heat pump wasn't wired in. It was just a blank cable. Where we've kind of been experimenting, uninstalling and reinstalling stuff, it was just a leftover part of the experiment. So anyway, that's wired in, and then this kind of, all that jittery stuff stops. Actually, let's just zoom in on that. Yes, so see where the flow temperature is jumping up? That's where the dip, actually the heat pump output is going below zero because we're exporting heat
to the outside.
Because the zone valve wasn't closing. So then I realised we had to finish installing the zone valve. I didn't know it was uninstalled. Amazing bit of information from your kit there. So not only were we heating the building solely from solar thermal, we were just warming up some of the planet as well, just to keep winter a little bit more mild. And then that was eventually resolved around here, and then I just did a couple of experiments here where I was opening and closing the zone valve to make sure it worked. And as I did, the flow temperature sensor up by the zone valve there heated up, and then it cooled down, and then I opened it again, and then it cooled down. It warmed up the sensor, and then it cooled down again. So that's what those little anomalies are. All of this stuff here is the buffer temperature, essentially, which is now down at 30-ish, somewhere around that. However, the building from 11 here all the way up till 5:30, which is 7.5 hours, has been solely heated by solar thermal. Okay, so essentially we've just been very lucky today, and we've demonstrated that solar thermal has a place and it can heat a building while the sun's shining. But also don't forget, we've washed dishes today. Harrison, the cameraman's eaten. You've eaten. We had a few others ate, and we washed up and whatnot. So we've had some hot water out there, but an absolute success. And thank you so much for coming and doing this. Really appreciate it. And it's like the whole thing's just blown my mind, because I was looking forward to analysing the data, but finding stuff that was wrong straight off the bat and already improving the efficiency was I'm chuffed with. But I can see a lot of power here and where this can go. So yeah, thank you very much appreciated.
Yeah, no
and
problem.
if you guys want to know more about I always get the name wrong. Open Energy Monitoring, which needs a better name. Go to openenergymonitoring.org.
That's it, yeah.
And Tristan sells this stuff along with his partner Glenn. He sells you all the kit so you can install it, monitor your stuff, tinker with your stuff, and get more efficiency as we have done today. Anything to add?
Yeah, we've got some really good data just in the last few days, and it's been really interesting for me just to see a different heat pump, valent heat pump, see what that's doing, and then see the interaction with the solar thermal. It's like there's a lot to learn there, which is great.
Yeah, and the heat pump, like the valence bit, it's impressive, isn't it? It's an impressive bit of kit. Yeah, thanks so much again. And we'll drop a link to Open Energy Monitor down in the description, as well as any other relevant links for today's show. And I'll see you next time. Cheers.